Let's talk now about two issues, overfitting and underfitting. So we're choosing this f from a particular universe of f's. Let's say, for example, that we have a data set where we're trying to predict some y given an x. So this is what we call a regression problem. I'll talk more about that in a future video. So, for example, this might be, for instance, square footage versus house price. Okay. And let's say that we have some particular data points. So let's say something like that. So we've got these 5 values. If we were to try and fit a linear model to these values, we're going to have a fairly high error, right? So we might have a, let's say the best linear model might be something like, I don't know, that, for instance. This would be an example of underfitting. So underfitting is where we have error due to a model that's not powerful enough. In this example, what we're saying is a linear model doesn't have enough power to capture the data here. A better model might be something like a quadratic. So here we have a quadratic. And we can see with the quadratic, we'll have very low error, while the linear model has high error, right? The quadratic may even go exactly through those points. So underfitting means we have this error to a model that's not powerful enough. And the solution is more powerful model. How do you know when you have this? Well, you go ahead and test. You look at your loss. Right? As we're going through and we look at our overall loss and we say, how does that loss compare, let's say, to a human accuracy on this problem? So how well can a human do in modeling, for instance, house dollars versus square footage? And if a human can do better, then that probably means we're underfitting and we need to make a more powerful model. As we work with neural networks, we're going to see we have much more power than just linear or quadratic or any polynomial. But for the moment, we're staying in that realm of polynomials. Now, on the other hand, what is overfitting? So to discuss overfitting, let's go ahead and add a few more points to here. Let's say we've got something like this. So we've got 2, 4, 6, 8, 9 points. Before we look at that, actually, let me tell you a story. So in my first calculus class, the professor asked a question of the class. And the question was this. Let's say you're given the sequence of numbers 1, 2, 3, 4, 5, 6. And his question is, what is the next number in that sequence? Well, like everyone else in the class, I said 7. But he said, no, actually, the formula I have in mind for this would be 727 was his answer. So we were probably thinking of some sort of a, f sub n equals n. He described the formula that he actually had in mind, which is f of n equals n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 times n minus 6 plus n. And so therefore, when n was 1, 2, 3, 4, 5, or 6, this first term was 0. And so we just ended up with n. But as soon as we got to the 7th term, now this was 6 times 5 times 4 times 3 times 2 times 1. That is 6 factorial, or 720 plus n. So the moral of the story is, with a complex enough function, you can actually match any sequence and get any value you might want. Or really, let's just say the moral of the story is that powerful functions have a lot of power in them. In this case, we have a into the sixth term, so it's a degree 6 polynomial, and that's very rich. As we go back over to this example, let's just look. If we wanted to get 0 error on these, we could go ahead and set up a, let's say, this is a 2, 4, 6, 8, 9 points. So if we had, let's say, a 9-degree polynomial, maybe it's something like this. Okay? And we could end up with 0 error. The problem is that we don't want to end up with 0 error on our training data. That's not our goal. Our goal in machine learning is to actually come up with a function that will generalize well to x's we have not yet seen. So what's important is that if we go ahead and add in some more points that we'll see in the future, we would expect those might be, let's say, here, something like that. And those points do not match to this 10-degree polynomial extremely well. So what happened is that our function overfit. So what we can say is that our training error is low, but doesn't generalize well. And that's our real goal. Our real goal is not to just get low loss in our training. Our goal is to also get low loss on other examples which we have not trained on. That's generalization. So how could we know when this happens? What it means to generalize well is basically to try this function on x's and y's that are not in the training data set. So try an x, see what the y hat is, see what the actual y should be, and see what the loss is. So the idea is we have 2 data sets. We have the training data set, and then we also have a validation data set. And the idea is that we only train on the training set. So let's back up. What we actually will normally do is take all of our data, our labeled data that we have, and we'll break apart and separate some of it. So we'll randomly select maybe 20% of it to be held back as a validation data set. And then we'll do training on the remaining 80%. Once we get low loss, we can then go and evaluate the loss on the validation data set and see whether it generalizes well or not. Let's look at a chart of time. So this is training time and loss. And we're going to look at 2 different kinds of loss. We're going to look at the loss of the training data set. So the training loss is normally going to start out high and go down and eventually asymptote. If it asymptotes very high, that's a sign of underfitting, where we've got high loss, and the solution again is to make the model more powerful. If we're talking about neural networks, as we'll get into that, we can see we can add more neurons, add more layers, add more weights, things like that. And then we can also look at the validation loss. Normally, you would never expect the validation loss to be less than the training loss. So let's say it'll be somewhat more. And in an ideal world, it'd just kind of run right below here. But what normally really happens is the validation loss also decreases, and then eventually it'll start increasing. What's happening here? This is where we are overfitting. We're no longer generalizing well. What's happened is, one way you can sort of think about it in this example is that the function is memorizing its input data. Right? That's kind of a one way you can imagine that a network can do poorly. Let's say it's doing happy faces and sad faces, and instead of actually getting the idea that it's smiles and frowns, it's really just taking the images you give it and just capturing, oh, if I see this particular combination of pixels, I know it's image number 1, and image number 1 is happy. And this combination of pixels is image number 2, and image number 2 is sad. That's not really what we want. That's not very generalizable, although it certainly leads to low loss. So what we want to do is, this tells us whether we are overfitting or not. If we look at here, let's look at the validation loss and the training loss. And let's just look at kind of high training loss and low training loss, and high and low validation loss. And let's just kind of look at these quadrants and see where we are. Low training loss and low validation loss. That's great. That means we have got a good model and it generalizes well. So this is where we want to be. If, on the other hand, we have high training loss, well, high training loss and low validation loss is very unusual. It's just hard to imagine how that could be, except some kind of random rolls of the dice. So pretty much, though, this doesn't happen. High training loss and high validation loss shows that we are underfitting. And low training loss and high validation loss says that we are overfitting. How do we solve overfitting? So, solution. Really, there are variable numbers of solutions. One solution we can do is reduce the power of the model. That is, when we're training, we have theta, all these parameters. We want to have fewer such parameters. If we're talking about a polynomial, we have a smaller degree polynomial, for example. Another thing we can do is add more data, add more training data. Given the power of the model, given the parameters that there are, there's a limit to how much can be memorized. And so as you add more and more data, that's going to cause it to have to learn based on actual aspects that generalize well, rather than just relying on memorizing particular parts of the data. So you can imagine here, if we have added 1, 2, 3, 4, 5, 6, 7, 8, 9 more data points to this, then all of a sudden this 10-degree polynomial is really not going to look too good. Likely we would end up with something, I don't know, more like, so even if we had a 10-degree polynomial, we are going to be less extreme than we were in this green case here, where it was only matching the blue points, where here we're also trying to add in the orange points as well. So we're not hitting every point correctly. We still have some error, but the error is fairly low, and our hope is that it'll generalize. And as we add more and more data, this pink line is going to probably smooth out more and more. There are other solutions as well. We're going to look at regularization later. This is a way to reduce power of a model. And the other thing we can do is what's called early stopping. That is, we just keep training until the validation loss starts going up again. And that tells us we overfit. So stop here, keep the values of the parameters that we've got at this point. So this can tell where you've gone too far, and as long as you've saved that previous value, you know what to do. A lot of what we're going to be looking at is how, in this class, is ways to prevent overfitting. But this chart is very useful, this table, in terms of just keeping in track the relationship between the training loss and the validation loss. And this chart is useful in seeing typically the progression of what training loss looks like versus validation loss. It is really important that your training and validation data sets be independent. So you often will want to just randomly pick a set of these, but there are cases where you can get in trouble where you are going to be training your model about things that will be in the validation. An example would be a challenge that was done, where basically they had a camera inside, forgive me for this, let's see. So, inside a car. I'm not sure why this person has antenna, but in any case, they had a camera facing into the car, looking at the car. This is for self-driving purposes. And looking and seeing what are people doing? What is the driver doing in the car. And so they had a bunch of different people and snapshots of these people, and we'd say like various possibilities where the person was looking ahead, the person was sleeping, the person was putting on makeup, the person was, looking at their phone, all those sorts of things. And what they had is the same person in lots of different poses. So here we might have the person reading the phone, and then we had a different picture. Right? These were really normally just pictures of the face and the upper torso, which was, this is number one. Number two, they were, let's say, putting on makeup. And number three, they were just looking ahead. So you might have, let's say, 10 different pictures for one person. And then there was a second person. So we had person one, person two, person in. And for each of those, we had K different pictures, each one labeled. So here is the key. So N, K instances. And you might think, well, okay, we'll just randomly take 20% of them and hold them back for validation. The problem with that is likely we would end up with pictures of every single person in the training data set. So we would have this green person in the training data set, we would have person one in the training data set, person two, all the way to person N. And the validation, of course, would have those people as well. The problem is, now all of a sudden, we have trained our model to easily recognize this person. So it's a lot easier for this model to distinguish between reading on the phone or putting on makeup or looking ahead when they already recognize this person. So instead of randomly choosing from this entire matrix, what we would really want to do is choose, let's say, 20% of the people and 80% of the people. And that way, we're training on one set of people. Our validation is on completely different people that we're never trained on. Because that's what we're trying to generalize to. Right? We're trying to generalize this problem to we have a camera in a car, and we're looking at a person we've never seen before, and we want to see what activity they're doing. So it would be cheating for the model to already know the people and just have to figure out what they're doing. So that is overfitting and underfitting. We've talked about how to fix an underfitting, ways to fix overfitting. We've talked about what to do in terms of how to tell what situation we're in based on the training and validation loss. And then we've also looked at what happens to validation over time. One morning we are going to actually see a third data set, normally called a test data set. And this is a set of our data that we've held back even farther. We'll get into that in the further. But just note that that happens. And on rare occasions, when you look in the literature, sometimes what most people call the validation set, other people call a test set. So just keep in mind, we're normally going to be using two data sets during our training process, one for the training and one for evaluating the generalization of that training. We call that second one validation. A few people call it test.